It's my pleasure to introduce Alexander Hulpke, who will be talking at our seminar. So thanks everyone for coming or joining us online or watching it on YouTube. And so our speaker today is Alexander Hulpke from Colorado State University, and we'll be talking about perfect groups of order up to 2 million. So there will be quite a few of them. So hopefully we'll go through all of them.
Yes, we will look at all of them in detail. Right. Yeah, good afternoon, or whatever time of day is where you're listening from. Thank you very much for the invitation to talk. It's been the invitation to visit. It's been a pleasure to be here. Yeah, so this is some work I did over the last few years on enumerating perfect groups. Before getting to this, my brief, so this is published in Mathematics of Computation, came out this spring, the brief shameless advertisement. This is a new journal, open access, where I'm editor-in-chief, and if you're interested, let me know and we can talk more about this. So, one of the things mathematics tries to do is to classify objects, and sometimes indeed by listing them all, or at least to have objects classified well enough to describe them by a theorem or as a list. And this is particularly enticing for discrete objects, and the total number of objects obtained is not so much really the goal. The goal is the process, the fact that one can do it, because that means you have enough information to actually perform that classification. And in group theory, the very natural class, at least finite group theory, the very natural classification is classes of groups up to isomorphism. And if they're finite, there are finitely many of them, so you can hope to actually have an exhaustive list. So, famous classifications with a computer, there is the work of Eamon O'Brien, 1990, on classifying P groups. The idea was extended around 2000 by Bettina Eick, Hans-Ulrich Besche, and also then with Eamon O'Brien on classifying solvable groups of small order. And together with Max Horn, Bettina, we extended this a little bit more in a more recent paper. So there the status is that with some exceptions, and these are basically large prime divisors, groups of order up to 20,000 or so are more classified. If you wanted to go further, you could easily go further. There is just an obstacle. Once you have a prime to a power more than 7 or 8 or so, then the total number of groups gets bigger, and that becomes harder. And basically it chokes. At some point the classification just chokes on the total number of groups. But what can we do if we want non-solvable groups? The whole classification process basically works in the same way. There is nothing in the construction process of the solvable groups which really uses solvable. The only place where it used solvable has been by in implementations of algorithms which only were available for solvable groups. Well, there is, in fact, however, there is a classification of perfect groups which existed before. This was done by Plesken and Holt, and a description of it you can find in the Handbook of Computational Group Theory, what the process does. They classified in 1989, it's published, so this is basically before my work, before I became a professional mathematician. This was just when I finished high school, when the work was done. They did it up to order 10 to the 6, but they had some exceptions of orders where there were too many groups. They used very clever theory, but it wasn't fully automated. And I will say a little bit more about that later. Yeah, as I said, it was done when I was in high school, and then for more than 30 years, no one managed to extend this list, which I always thought was a little bit embarrassing, that a lot of other group classification results slowly got extended as computers got more powerful. This has been, I think, as far as classification of finite groups goes, the result which for the longest current time has been standing without extension. And that's what I want to extend now. So the goal is I want to extend this existing database, well, in part just because one can do it, in part because these groups actually can be interesting examples for studying conjectures. I want to verify the classification, which was done very much by hand through automating it. It's in some way a prototype of constructing non-solvable extensions, and it showcases the underlying tools, constructing extensions, constructing permutation representations, isomorphisms, and documents the improvements in the gap implementations of these tools that actually made it possible to do this. This is implemented. There is even the code available on GitHub if you're interested in doing it or running it further. So how do we do this? Well, since I'm from Colorado, I thought I'd start with a picture of a mountain. If we have a problem, say we want to climb up a mountain and we can't climb that high, how do we try to get to a higher mountain? Well, it's very easy. We first climb a smaller mountain, that's known groups of smaller order, and then we just lift the smaller mountain up and we are on top of a higher mountain. And that's exactly what I want to do. I take the existing groups of smaller order, I put modules underneath, and these extensions are larger groups. So what I want to construct are extensions. So if let's look for the construction process. Let's say I want to construct perfect groups of a particular order n. And these groups, one of them I will call E for extension. Well, this group E, I'm going to look at its solvable radical, the largest solvable normal subgroup. This largest solvable normal subgroup might be trivial, then for the order restriction I have, and in fact it wouldn't just be up to 2 million, it would go, the first case for something more interesting would be happening, would be order 60 to the 7. Then with the extra condition of having to be perfect, the only thing possible is that the group must be then a direct product of the groups. This is not a necessary, I could look at non-solvable groups and then would have to look at more possibilities for the groups without solvable radical. In this case, it's just very nice to describe. It's just direct products, and we all know how to enumerate direct products if we know the input. So of course, implicitly, I'm using the classification of finite simple groups to give me the possible simple groups that can occur. Well, otherwise, there must be a minimal elementary abelian normal subgroup. Yes, solvable radical is not trivial that it has a solvable normal subgroup, so it must have a minimal non-trivial solvable normal subgroup, and that must be elementary abelian. I call it M for module, and the factor of a perfect group is again a perfect group, so the factor is a perfect group of smaller order. So that would be the analysis. The synthesis would be the other way around. I take a perfect group G of smaller order. Maybe I should point with a mouse and not with a finger so the online people can also see where it is. I can take a perfect group of smaller order. I take a module for that group. I form the extension, and if I form all possible extensions, I forget all possible perfect groups of the structure. I'm not claiming every extension is perfect. If the extension is the direct product, for example, it will not be perfect, so I always need to test for the result being perfect. I'm just claiming I get all of them. Yeah, oh yeah, and I should have said the solvable radical is the largest solvable normal subgroup. Yeah. So how does the construction process work? I start by forming direct products of simple groups so that I get order n, that is taking a list, just combining them. Then I'm taking all possible divisors k of n, and I take the list of perfect groups of order k, if there are any. If not, then k can be discarded. For each such group, such perfect group of smaller order, I take the simple modules of order n divided by k. Why is it sufficient to look at simple modules? Because every module can be built from simple modules. So if I have an extension with something non-simple underneath, I would construct it from a larger factor group with a simple module on the bottom. And then for every module, I form all extensions. I test whether they are perfect. Well, and there is no guarantee that every isomorphism type will be only constructed once. I might have constructed the same isomorphism type multiple times, so I need to eliminate isomorphic copies. And that is basically...
Sorry, can I just interrupt for a moment?
Yeah.
So you have some steps here, but these, one is sort of independent of the others, is that
Yes, yes. The one is the one world and the others are the other world. Yeah, but that would be the full construction of all. Yeah. And of course, some of the things I need to tell you how to do this. So let's start looking at the simple modules. How can I get the simple G modules there? I'm using the theorem of Burnside and Brouwer, which says that if you have a single faithful module and you tensor it up and look at constituents and continue tensoring and looking at constituents until you don't get any new isomorphism types, that will give you all irreducible modules. Burnside proved in characteristic 0, Brouwer proved it in finite characteristic. And in GEP, there is a command irreducible modules that will do this. And for the orders we are looking at here, this typically works very easy. I have the groups as permutation groups, so the faithful module I start with is just the natural permutation module. Well, there is eliminating the isomorphic copies, and that is something which generically might be hard, and that is ultimately basically the hill on which any classification will die. Not just classification of groups, any kind of combinatorial enumeration. The isomorphism tests are the killer if you don't do them cleverly. Because if you have A groups you want to eliminate isomorphic duplicates, in the worst case you might have to do A choose 2 tests. So this will be quadratic in the number of groups. So the number of tests very quickly increases as the number of objects increases. And to make this enumeration feasible, we really need to cut down on these isomorphism tests. Well, and there is the extensions. So let's start by looking at the textbook case of group extensions. A group extension is a short exact sequence where I have the group E as an extension of a factor group F with a normal subgroup N. I identify this normal subgroup with its image in E. I choose a transversal tau from the factor group to E. I want that the transversal element for the identity is the identity. Otherwise, I just need to do a stupid coordinate change all the time. And I want to represent elements of the extension as pairs, element of the factor group, element of the normal subgroup, which should represent the product of the corresponding transversal element with the element of the normal subgroup. The difficulty is, unless the extension is split, and that's why we only do split extensions in the beginner courses, then the transversal is not a homomorphism. If I take 2 transversal elements and I multiply them, the product is not guaranteed to be a transversal element, but I get these cofactors MAB, and with these cofactors, then I can write out the full multiplication in the extension. That's not particularly interesting. Sorry. Yeah, so these cofactors, they are the crucial parts to actually describe the multiplication. They describe how apart from the action of f on n, how the group extension differs from the semi-direct product. Well, and that can be done in the case of an abelian normal subgroup through cohomology, which in some ways is just a fancy word for linear algebra and a little bit extra. So if we have an elementary abelian, or actually elementary I just need for linear algebra, because linear algebra all over Z modulo 4 or so, I need to handle the zero divisors. Yeah? So if I have an abelian normal subgroup, I can look at the action of the factor group on the normal subgroup, and that will only differ that will only depend on the factor group element, regardless what transversal I'm choosing, and that's where an abelian comes in. I will write the normal subgroup then additively. So these cofactors which I need, I will consider them as what are sometimes called cochains. These are maps from F cross F to N. Yeah, they take an input, a pair in F cross F that is AB, and they assign an element of N that's this MAB. And associativity of the group multiplication in the group extension gives this co-cycle condition here. It's formally the kernel of the co-derivation map. Yeah, so we get these co-cycles. And the problem here is this equation crucially involves three variables. That's because associativity is a condition which involves three elements. I can't avoid using less than three variables. But that means I would need to run through F cross F cross F. And that is a huge search space. The other thing I can do is I can ask with what happens if I'm changing representatives so I change my transversal by changing representatives. That gives me the co-boundaries, again, which I could describe through in a more formal setting, homological setting. And the theory tells me that the two cohomology, the two co-cycles modulo the two co-boundaries, they correspond to equivalence classes of extensions. Now, if you start looking at textbooks, they give you that theorem, and then you ask, are there examples? And they give you two kinds of examples. They give you the example of cyclic groups. In the case of cyclic groups, things turn out much easier because you basically have just single elements and the rest is powers of the element. You don't need to consider them separately. So cyclic groups, that is easy. And they give you cases when the extension is always split and you don't have any interesting extension structure. They don't give you other examples. And why not? Because it is such a pain to write down these possible cofactors, MAB. Yeah, so the books don't want to spend writing out 3-4 pages for an example. Yeah, so that's the one caveat. The other caveat is equivalence classes are not group isomorphism. Equivalence classes are equivalence of extensions, which is basically commutative diagram between two short exact sequences with the N and the F connected through the identity. So that is less than isomorphism. So there will be isomorphism tests left, which one has to do. Yeah, this 2, there are maps from G cross G to M. And as I mentioned before, this is a huge space if I just want to search. I should mention that there is, again, a relatively early computational paper from 1985. This was when I was just starting high school, where Derek Holt describes a very nice algorithm for calculating cohomology. It's a very clever algorithm. The problem of it is that there exists basically one implementation, and that is by Derek. And that implementation is starting to show signs of bit rot, in the sense of that it isn't completely trivial to compile it any longer on modern machines. It has hard-coded size limits in there, which were completely sensible size limits in 1985, but we now have more than 16 kilobytes of memory and so on. So these are the problems. And I mean, it's a really, really clever algorithm, but it is very subtle. And the subtlety is that he uses a co-restriction map, which goes from the cohomology for a pseudo subgroup to the cohomology of the whole group. And to write down that co-restriction map explicitly, there are dependencies on choice of representatives, which are really tricky to get working. So I've tried to implement this 15 years ago and I failed on it because this choice of representative was too subtle. So I want to do it in a somewhat different way, but this is not to take away from Derek's really nice algorithm there. So what I want to do is to describe a somewhat easier way of calculating cohomology, which actually by now works well enough on the computer for the examples, at least I've been interested in. So let's reduce it to generating sets. So in the extension, I said the elements are pairs, factor group element, normal subgroup element, and the pair G, 1 is the chosen coset representative. That's what the transversal map would do. The two co-cycles describe how the multiplication happens. Yeah, if I multiply a representative, I get the representative of the product times this cofactor. And I now choose a generating set for the group G. Every element can be written as a product in the generators. Yeah, here I don't write inverses there, so if you want, assume that the generating set also includes inverses of the generators. And what I now would like to do is to simply say, for every element in the group, I find a word, an expression as a word in generators, and I want to define the representative for this element, just the corresponding same product of representatives from the word expression for this element. By doing this, I set an enormous number of these cofactors to be trivial, because if an element is defined as A times B, its representative will be, in this definition, the representative for A times the representative for B without a need for a cofactor. So that's the reason for doing this. This is a choice I can make, and I want to make this choice to kill a lot of cofactors. Well, to do this, of course, I need to write the elements uniquely, because if I choose different word expressions, I might get different representative products, and then I can really do this and write it this way. So I need unique word expressions for this. I need normal forms of elements, and the mechanism for this is called a rewriting system. Formally, rewriting systems are set in monoids, but for what I'm doing here, basically, you can ignore the fact that a monoid doesn't necessarily have inverses. So this is a tool from, if you want, theoretical computer science or automata theory or so, for monoid theory, for finding a normal form of elements. I want to transform a word in generators into a unique normal form. So how am I doing this? If I look at it as a finitely presented group, I interpret relations among generators as rules. So if I have that two words represent the same element, I interpret it as a rule that a word A gets transformed into a word B. That means every presentation can be considered as a rewriting system. What is the normal form? The normal form is simply that I reduce as long as I can. And I will denote this by this arrow star. So I just look at, does any rule apply? If yes, apply it, make it smaller until you can't do any longer. Of course, I want that it should terminate. So for termination, I need a couple of technical conditions. I want a total ordering of the words. I want that these rules are always bring the larger word to the smaller word. I want that this ordering doesn't have infinite descending chains that will give me termination, that I can't reduce infinitely long, and I want that the ordering is compatible with forming products, because ultimately I want to apply it to products of elements. An example would be first length and then lexicographic. Now, of course, there could be ambiguity. The ambiguity can arise if I have two possible reductions. And I think I have this here. Oh yeah, and I should say in the free group, the rule corresponds to an identity in the factor group. So I'm slightly sloppy here in writing. There it's an identity in the factor group. This is a rule in the free group. So what I might have is a situation that I can reduce a word in two possible ways. That can happen. Well, if I want to end up with a normal form, I must have that I can then reduce both results from these two different reductions further on to something completely reduced, which is the same element. I must have this condition whenever I have two choices. Otherwise, I'm not guaranteed a unique normal form, and then it's not really a normal form if it's not unique. If this condition holds, I call the rewriting system confluent, and the important result is that it is sufficient to test for this ambiguity only on overlaps of words. So if I have a word left-hand side A1 and the left-hand side A2, of two rules, A1 goes to B1 and A2 goes to B2, I look at overlaps of these left-hand sides, reduce them in both ways. So that overlap would be the W. Reducing this bit would give me the X, reducing this bit would give me the Y, and then I must have that with all the rules together, both forms can be reduced to the same end. If this is the case, the rewriting system is called confluent, and then there is a theorem which says that I get a unique normal form. Yeah. While every presentation gives me a rewriting system, it does not necessarily give me a confluent rewriting system, because there is no need for this condition to be fulfilled. For finite groups, I could just encode the whole multiplication table and thereby get a confluent rewriting system. So existence of confluent rewriting systems is trivial. So how can I make a rewriting system confluent? I can do so by adding rules. So if I look at the situation that I have ambiguity and I have an X and a Y and I can't reduce them to the same element further, yeah, I have the non-ambiguity, well, then X and Y must be different words. One of them must be larger than the other because I have a total order. So I can add a further rule, which would say, in that case, x should reduce to y, and then I have forced this situation which I want, because the element, no, that doesn't help anyone if I point to my laptop. That element z I wanted to have is now just this element y here. Yeah? So I just add a new rule and thereby avoid a conflict for this one overlap. That now cleans out nicely. But I add new rules, and add a new rule. The new rule gives me new overlaps, so I must repeat this. And that is a method which is due to Knuth and Bendix. This is the same Knuth as with LaTeX and the art of computer programming and so on. Well, it's a method because it's not guaranteed to terminate if the group is, or the monoid is not finite. If it is finite, or in general, you can't predict how long it will run. What it says is you run through all pairs of rules, look at all possible overlaps of the left sides in all possible ways, reduce both ways, reduce them further to irreducible elements x and y. If they are different, you add a new rule, or the other way around, if y is the larger one. And I repeat and I continue doing this until no new rule arises. And if at some point this ends, that I don't get any further rules and all overlaps are handled, by definition of this process, then all overlaps clean out, reduce in both ways uniquely. So if this terminates by definition, I must have a confluent rewriting system. This process of handling overlaps is very similar to what Gröbner bases do. Gröbner bases, there the overlap is described by the S polynomial. So in a certain sense, this is exactly conceptually the same idea. It's just in the non-commutative setting, we are not guaranteed that it terminates, while Gröbner bases have exponential but have a given runtime. So we can find such confluent rewriting systems for groups. Basically, to do so, we just would need to reduce to the case of simple groups, and one can write them down using, for the ones of Lie type, you can use the BN pair structure. For alternating groups, you can use the Coxeter presentation with a little bit extra decoration, and the sporadic ones is just a finite problem where you can work through the cases one by one, though I haven't done so for Baby Monster or Monster. Yeah, so how does this help me for the extension? If I have a product of two representatives for factor group elements, I now can assume that the factor group elements are written as words and generators. So if I want to form this product, I now just have to take the product G times H as words and generators and to bring it into normal form. But we are working with cosets, so now each rule A goes to B that is an identity in the factor group gets an extra tail, an extra element of the normal subgroup. If you know what a PC presentation is, it's exactly the same idea as with a PC presentation, just generalized to a case that doesn't require cyclic factors. And therefore, and if I know these tails, I can bring every word into normal form. So I only need these cofactors as functions from the set of rules to the module. So I have a much smaller support on where these cofactors are given. Instead of a set of size order of the group factor group squared, I now just have a set of these given on the set of rules. This is much smaller. One can show that one still gets the same quotient group, still the second cohomology as a quotient group. And why does this work? I could take generators for the module. I take obvious generators, a basis for the module. I take rules that describe the module structure so that pth powers of elements are trivial, that the elements commute. And on the set of generators for the vector group and for the module, I write down an extended set of rules. I take the rules for the module. For every generator of the module and every generator of the vector group, I have a rule that brings a product in the wrong order, mg, into a form vector group generator times module element. And I can do so because the M is a normal subgroup, and using something called the Reith product ordering, this gets it down to a smaller element. And I take the rules with a tail, which I just described on the previous slide. Together, one can show that this together then will give me a confluent rewriting system for a monoid, in which every element has an inverse, so it is a struct group, and it is a group with a structure of such an extension. So that's how I can write down such a rewriting system for the extension. And, oh yeah, well, the verifying one has to do, this is not trivial, but one can do so. So let's look at this in an example, because I think that is easier to see than writing it down formally with indices. Take the dihedral group of order 18 as an extension of a normal subgroup of order 3 with a symmetric group S3 on the top. A confluent rewriting system for this vector group S3 is given by this Coxeter presentation. The normal subgroup is generated by a single element. It's just a one-dimensional field, and both generators of the vector group act as inversion. So how I can describe an extension by the extension as being generated by the two generators for the vector group, the generator of the module, the generator of the module, and now I have the rules for the module. That's just one generator, which has order 3. I get these ordering rules that MA is mapped to A times something, and B is mapped to something, and these two rules describe the action of the vector group on the module, and the rules from the rewriting system of the vector group get modified, and actually the only modification I need to do is to the third rule. The first two rules stay the same, and if you take these two generators as depicted there as symmetries of a 9-gon and M being the 120-degree rotation, that exactly describes this dihedral. Now, how can I find the possible tails? I look simply in this context at the tails as variables. And what I need is confluence. So the confluence conditions are necessary conditions on the variables, which the variables need to fulfill, and that ultimately will give me linear equations in these tails as variables, and the solutions will describe the two co-cycles as restricted to the rules. I quotient out the two co-boundaries, they are easily found from the definition, and I get the two co-cycles, and I even have, through the rewriting system, a presentation that is a presentation for the corresponding extension. This is something which in principle has been known for a long time in folklore, but never was, to my knowledge, was never properly written up in a paper. Heiko Dietrich and myself in a paper in the Journal of Algebra 2021 in the last section give formal proof of this, just so that it is will exist in the literature. So that allows me to calculate cohomology. I might want permutation representations. What I'm doing there is basically that I try to look at subgroups of the factors, so subgroups of the extension that contain the module. I want to look at linear representations of this subgroup because I can find them easily with finitely presented group methods, and then I induce up the linear representation to the group that often gives me suitable permutation representations. So let's look at this again in our example. So I want to take S3 acting on the one-dimensional module over the field with 3 elements where the module action is given by the sign. So what do I need to do? I need to take the rules for the factor group and add tails on the right-hand side. So x, y, and z are the variables. I also have the rules for n. I have these rewriting rules that describe the action of S3 on F3. I didn't write out these rules on the slide. So what are the possible overlaps? I can overlap A square with itself by writing it as A square A or as A square, reduce it both ways. A square reduces to AX because A square becomes X. A square A reduces to XA, which using the action is the same as AX inverse. So I get from this that x must be x inverse or must be equal to minus x. If I write it linearly, the same from the b square rule gives me that y is minus y, so x and y have to be 0. The other overlap I can have is BAB overlapping with b square, that is this overlap. I can have B square AB as another overlap of B square with AB, and I can overlap BAB with itself as BAB, and they basically don't give me, this gives me a condition involving Z, but the condition becomes empty because I know already that X and Y both have to be 0. So my solution space is a one-dimensional space. I can choose Z as I want. X and Y have to be 0. That solution space describes the possible 2 cocycles. I know that the solution space must be at least one-dimensional because I've given you the dihedral group as a non-split extension. Yeah, so the 2 cohomology group can't be trivial. And here I've explicitly calculated it. So what we know from this is basically there are potentially 3 non-isomorphic extensions, the semi-direct product, the dihedral group, and there would be potentially another one which would come by choosing not 1 but -1. So after this theory, let's go to Geprode and look at what it is concretely on the computer. So here I'm taking the symmetric group on 4 points. I'm calculating irreducible modules over the field with 2 elements. I'm picking the second one, which has dimension 2, and I calculate the 2 cohomology for this module. The function is called 2 cohomology generic, and that is a slightly awkward setup because 2 cohomology on its own was defined with a particular syntax that only worked for solvable groups. So that's why it has the generic in the name. It returns a record with a couple of components. Now, what information am I storing there? I have rules from the monoid, and some rules in the monoid are just rules that describe that I have a group, so that every generator has an inverse. These rules are not interesting. They just carry through. The interesting rules are the rules in position 1, 2, 3, 7, 8, 9, and 10. These are the rules that can get tails. And now there are 7 rules. So I have 7 tails. Every tail lies in a 2-dimensional module because it's an element of the module. So the whole system must live in a space which has dimension 14. Let's build such an extension, this last argument true here. So I take this cohomology record, I take a vector from the cohomology to build an extension. The true just says build permutations. What it does is we take these, here we have relators, they come from the left-right rules just by writing left inverse times right. Okay, so let's look at these monoid rules. So I have A square is the identity, B square is the identity, C square is the identity. It's the Coxeter presentation for S4. Then I have some rules here. They are not interesting because they describe just that I have a group, not just a monoid, that I'm formally allowed to invert generators. But since the generators have order 2, they are their own inverse. So that's why they're not interesting. That's why I have 1, 2, 3. This is 4, 5, 6. They are left out because they're not interesting in this way. Let's look at this rule in position 7. That's the rule CA becomes AC. If I look at the cohomology vector here, in the 4th position, so the 4th pair, I have 0, 1. That means the rule CA transforms to AC. Now is the rule CA transforms to AC times the element M1 to the 0 times M2 to the 1. That's what the 0, 1 tells me here. And indeed, in the extension, the corresponding rule written as a relator has exactly this form. So that's in probably more detail than you ever want to see how the extension structure exactly corresponds to the groups. So let's go back to the perfect groups. If I do this construction process, and now with this, it's really easy to implement. That function is basically doing the whole construction process. I go through the divisors of the order. I go through, well, apart from the direct products that is left out here, I go through perfect groups of smaller order, calculate modules, calculate cohomology, run through the cohomology group, form the extension. If it's perfect, I add it to it. Yeah? If I do this, I just get groups that are isomorphic. So for example, order 15,316, I find 15 groups, but there are just 7 isomorphism classes. Or if I go to the next order bigger by a factor 2, I find 225 groups and 37 classes. Again, factor 4, I find 10 times as many groups. Yeah, so as the orders grow bigger, the factor between the groups I'm finding and the classes gets bigger and bigger. And that is this problem of dying on isomorphism tests. So how can I avoid isomorphism tests? First, I only count groups if they are constructed from a minimal module and minimal type of the factor group. This is an arbitrary lexicography that I test if a group is constructed but has another normal subgroup that is smaller or normal subgroup of the same order where the factor group is of the smaller, lexicographically smaller isomorphism type, I discard it. I can take an action of what are called compatible pairs on the cohomology group that will do some reduction which corresponds to nice isomorphisms that come from isomorphisms between both parts. I can try to eliminate isomorphism tests by grouping the groups together by invariance, number of classes, number of subgroups, and so on. And then there are some hard isomorphism tests left. Yeah, the nice thing with this lexicography is also that basically this will discard groups where the module is smaller. So I own, or the factor group type is smaller. So the only isomorphism tests left are amongst groups that are constructed for the same module and the same factor group type. So this big set, remember the A choose 2 isomorphism tests, which were hard. This big set now is split into many, much smaller classes, amongst which I only need to do isomorphism tests. And that's what makes it feasible. The isomorphic, the act that I mentioned, the compatible pairs, I think for time reasons I'll skip over this. So the isomorphism tests themselves, this is an algorithm of Cannon and Holt, which by now also is close to 20 years old. It uses a solvable radical approach, finding a characteristic series, isomorphism between factor groups, and then extending it to isomorphism of larger and larger groups. What has changed is that the implementation in GAP using the function isomorphism groups has improved in a very substantial way. The key ingredient there has been a permutation representation for automorphism groups, because at some point we need to search through the automorphism group for finding suitable elements. And that has been good enough to run this classification. So what are the results? This ran about 11 single core weeks on a processor with Geekbench 5 single core rating of 910. So that is half the speed of a new Apple laptop. It's a decent computer, but it's not the super fast, not the fastest you can get nowadays. I verified the Holt Plesken list. The counts agree. Well, that is good, both for them and for me. I found 5 missing groups in their list. And these missing groups really they're the kind of error where you say, oh, of course. So for example, one case where they forgot is a direct product of it's not direct, it's a subdirect product of 2 perfect groups of smaller order. Yes, it exists, it's obviously there. That's because they didn't do it, they did a lot of it by hand. It's the kind of thing, if your desk is full with papers, at some point something falls off the table on the floor and you forget it. So that's why it's really useful to do it with a computer, and why there are potential, why I feel that classifications by hand, even if done by very careful people, are problematic. On the other hand, it is impressive that this result, which really more than 30 years old, done on computers, which by now basically look antediluvian, how far they got. As a result, I got in total 15,768 perfect groups of order up to 2 million. They're available in GET 412 through the function perfect group. Why 2 million? Because this was twice more than what they did. If someone wanted, I could go further. It's just, okay, I have already almost 16,000 groups. If I would go up by another factor 2, it would be in total probably around 30, 40,000 groups. Do we really want all of them? But if someone really wanted them, they would be calculatable. You could just run this existing code of mine to calculate them further. Yeah, and that's all I have. Thank you very much.
Thank you, Alexander. Do we have any questions here from the audience?
Yeah, perhaps I'll ask a question. The list that was there since 1989.
Yeah.
Do you know? So it was available in GAP, did you say? Or how was it available?
now the groups they are available in GAP or in Magma.
Before now, how were they?
Before they were also available. The list is either available. It's a book by Holt and Plesken called Perfect Groups, which has a microfiche supplement where the presentations are written out. But for a long time, these groups were available in GAP and Magma. But just the list from Plesken and Holt, and I've just now extended the list. It's available in GAP. John Cannon has the list, and he gave them to Bill Unger to put them into Magma. I don't know what the current status is in Magma.
Do you know how many people cited this and
the old
depend on this list?
The old one or the new one?
The old one first.
It has a fair number of citations. I don't know how many really relied on completeness of the list. I think they have been more useful as examples of groups to have extensions that are not just semi-direct products. So I think that's how they have been used more. They are in some way, there are interesting conjectures by Derek Holt about number of perfect groups, but basically for that we are still far too small. There we would need to go to orders around not 10 to the 6, but 10 to the 10 or 10 to the 12 to start to get an idea whether how good his estimates are, or to try to estimate certain coefficients in his. He actually has a theorem about the number, but it has coefficients in there, which he doesn't give explicitly. So for that, we are far away from where the list would be useful for.
When you talked about the pesky isomorphism test, you had one slide there where you illustrated that for some size, so and so many results reduced to. Was there were the numbers just random, the 15,300 something that you had there? Why?
These are the numbers from the classification. These were the concrete,
So of order 15,360.
Yeah.
Why that number?
Why that number? Because that is 60 times 2 to the 6 or 2 to the 7. Yeah.
Which means that there will be more.
There will be extensions which are right. A perfect group needs to have something simple, non-abelian on the top. The smallest possibility is A5. That's why there is the 60. And now I want to put modules underneath, and basically for the same order I get most module bang for the buck by picking prime 2. That's why that order comes.
Okay.
Yeah.
Makes sense.
Okay. Do we have any further questions?
Yeah, I'll ask a question.
Yeah.
You said, I think if I remember correctly, when you answered an earlier question, you said if you double the number of groups you looked at, or size groups you looked at, you get twice as many. But
Very, very roughly.
you expect fewer, because you get fewer simple groups as you increase.
No, but it's not. It's the extensions. The simple groups are harmless. It's really the extensions that come there, and that is the two. I think one would actually expect a factor slightly bigger than 2, but the 2. It's not that horribly away from 2. So I think you get up to order 1 million. You got around. There were around 6,000 or 7,000 groups, and 2 million has these 15,000. So that's where my guess from 30 to 40,000 comes from. It's 2, and you give a little. You round up to something nice.
And did you say that Holt had a conjecture of what it should be in terms of?
Holt has a conjecture, well, actually he has a theorem which gives an upper and a lower bound. I don't, do you know there is a theorem of Higman and Sims which counts number of p group. I think actually even total number of groups of a given order. And they give bounds, upper and lower bounds. Do they give a lower? They give certainly an upper bound. Holt gives an upper and a lower bound, but he has constants in there. And the constants occur both in an exponent. So this is really, it tells you roughly that they must grow exponentially, but these orders are too small to make any real. Actually, what even happens is, so what he has is a quadratic polynomial in the exponent. And I thought, let's take the numbers I have and let's try to fit the quadratic polynomial. And the quadratic polynomial is both in the upper and the lower bound. Yeah, so it must be exponential in a quadratic polynomial. I've tried to fit the quadratic polynomial, and the best fit I could find was a linear fit. Yeah, so that tells me I'm not where something interesting is happening. I'm still not even on the runway. I'm just taxiing towards where something exciting is going to happen.
Is this because not enough like simple groups have shown up in a serious way?
I don't think it's the simple groups. I think it's again the simple groups, there really aren't that many. Yes, you get in some way at certain orders some new simple groups arise and you get extensions with them. But in total, I mean, that is not something which this is not part of Holt's conjecture or Holt's theorem, and I don't know whether I should dare to conjecture this, but I really wouldn't be surprised if basically the perfect groups which have a single A5 on the top, if they dominate everything. And that's like with interest. If you start early on, then the interest from investing $1 in the year 0, that will exceed any other investment made by now. That would have exceeded, even with minimal interest, any investment someone plausibly could have made in the 20th century, just because you have so much of a head start. And that's the same there. The A5 is so small that you can put more modules underneath. And that's where all the groups come from. They come from that there are so many different ways how you can form extensions. But going back to the initial question, what are they used for? Yeah, that's why I think that list is interesting, because it really gives you examples where you can say, okay, that is different things that can be possible with extensions, and where the theory of cohomology tells you, yes, they exist, but you don't have concrete examples at hand. These are concrete examples, and in some way, the easiest concrete examples of non-split groups.
Yeah. Because I was thinking like most non-abelian simple groups are PSL2 something.
Yes.
But you think there would still not be enough of them to beat?
There are not enough of them. And it's basically, if you look in the list, yeah, so you start with A5. So the next, you have already, by the time you have the next order 168, you have the 2.A5, the SL isomorphic to SL25, you have already one extension. By the time you get the next order, I think you have 360, you can have a 2.2.A5. And I think there you have already two possibilities how you can do this. Yeah, so that's why there are so many. And if you go further, and yeah, in some way that's these weird orders. It's the powers of 2 in there, and yeah, order 122,000. How many simple groups do we have there up to this order? Maybe 10, 15 simple groups, and a few direct products, A5 cross A5 or so. But, well, let's be generous. Let's say we have 50 simple groups and direct products of simple groups. In total, there are 258 classes. So it's the extensions that make it up.
Right, so is it true, or do you conjecture that for each simple group, the number of groups with that one on the top grows with a quadratic exponential?
I would guess so. In some way, yeah, probably I should say yes, I conjecture. I'm just slightly careful in using the word conjecture. I would expect that with the mod, I mean, you have for every group, you have modules that are non-split extensions. And if you have every finite group, if you take a perfect group and you take a non-split extension, you get again a perfect group. So the only thing that needs to happen is that your cohomology is either in characteristic bigger than 2, because then you have already the field elements, or that your cohomology has there must be modules where the cohomology doesn't have dimension 0, or where that your cohomology has dimension a bit bigger than 1. And suddenly you have tons of extensions, and typically just relatively few of them tend to be isomorphic. Or maybe that's a bit too strong. There can be a lot of isomorphism, but still enough of them survive. And so once you have a slightly bigger cohomology group, there are lots of them, and then the floodgates are open. all continues. So, yes, so I would expect that if you look at perfect groups with a given, or let's even say a given radical factor, that the total number will be exponential, but I briefly had looked at Holt's paper. It's looking at it in a bit more general case. I think he's not just looking at trying to enumerate these extensions. He has a somewhat better argument where he doesn't even need to look at the possible factor groups, but there must, yes, yeah. You can probably, I don't have a theorem at hand which says, oh, that must happen, or that's the reason. But the non-split extensions, this is one basically would need, one would need a theorem about the structure of the principal block of these groups, and there is probably no, I don't have a theorem where I can point to. It's just from experience, yes, definitely that total number should grow exponentially. And I mean, not for every prime, just for the interesting primes that you can get non-split extensions. And so you get also again and again the same kinds of modules. If you have, because the modular representation theory basically is the same for when you factor out the p-normal subgroup, that ultimately tells you that because to stay perfect, you need that the extension is non-split. And that basically tells you that it's always, if you continue doing it, it's always the same kinds of modules. So there might be modules that will never occur for a simple group that will never occur in any perfect group that has this simple group on the factor.
Okay. Well, if we don't have any further questions, maybe let's thank Alexander one more time for his talk.